Hello and welcome to Cashmatics. This is number 4 in a series of videos on complex numbers, and what we're going to be learning about today is how to multiply and divide complex numbers, or indeed square complex numbers, when they're written in modulus and argument form. And in fact, what I'm going to show you is a shortcut to getting there, and we're going to use some trig identities to get us there, but I'll tell you what they are in a bit. So grab yourself some paper and a pen and let's get started. Now the first thing I'm going to go through is some trig identities, and depending on whereabouts you are in your A-level studies, you may have or you may not have already come across these, but I'll put them on the screen for now. So the top one, the sine of A plus B, or the sine of A plus or minus B, is equal to the sine of A multiplied by the cosine of B plus the cosine of A multiplied by the sine of B. Now what you've got to really pay attention to is the signs over here. So if that's a plus, then this has to be a plus. And if that's a minus, then this has to be a minus. And the same goes for cos. Look at the signs. And what you can see here, if that's a plus, then this one over here is going to be a minus. And if this one's a minus, this one's going to be a plus. So it's really important that you pay close attention to the signs, because if you don't, then these proofs aren't going to make much sense to you. So let's start by defining two complex numbers. So we've got Z1, which is x brackets cos A plus I sine A, and Z2, which is y brackets cos B plus I sine B. Now, these are in modulus and argument form. So what we can determine from that is that the modulus of Z1 is x, and the argument is A, and for Z2, the modulus is y, and the argument is B. And what we're going to do is we're going to multiply these complex numbers together in the form that they're in, and then compare the result to the identities we've got at the top and see what we can deduce. To save a bit of time, I've just gone ahead and written Z1 multiplied by Z2 here at the top right. So that would be x brackets cos A plus I sine A multiplied by y brackets cos B plus I sine B. And because all these things are multiplied, it doesn't matter what order I write them in. So I've written them as xy, and then I've written the trig bits at the end. And what I'm going to do is expand those brackets and see what we get. Now I'm sure you're all capable of expanding double brackets, so I don't want to bore you with those sort of trivial things. And the result you get from that is cos A cos B plus I cos A sine B plus I sine A cos B plus I squared, so let's just say squared, sine A sine B. And what I'm going to do is write them in a different order again, and then compare them to the identities I've got over there in blue. So writing them in a slightly different order, all I've done is just written these in a different order, which is perfectly fine. Okay, I've written the cos A cos B and the I squared sine A sine B first, and then I've written the I sine A cos B and the I cos A sine B next. And what we know about I squared you should by now know is -1. So what we can do is we can change this part here to just minus sine A sine B. And what I'm going to do now is just compare these results to the identities. And if you look at this bit here, okay, that's exactly the same as what we've got over here. And we've got a minus here, so that's the same as this minus here, which means that is the cosine of A plus B. So let's just rewrite that bit. So xy times the cosine of A plus B. Add, now with these two terms here, I can factorize out an I, so that's I. And then I've got sine A cos B plus cos A sine B. And that's exactly the same as what I've got over here. So sine A cos B plus cos A sine B. So if that's a plus, that means that would be a plus. That's the same as the sine of A plus B. Okay, so what does all this mean? Now remember, the whole point of doing this is so that we've got Z1, Z2. And what that means here is that this number here is the modulus of Z1, Z2. And this here is the argument of Z1, Z2. So let's just generalize this result. So when we want to multiply two complex numbers, we would multiply the moduluses, or the moduli, however you call it, however you say it, but with the arguments you'd add them. So let's just write this result over here. So Z1, Z2, okay, the modulus of all that is equal to the modulus of z1 times the modulus of z2, and the argument of z1, z2 would equal the argument of z1 add the argument of z2. Okay, and you get a very similar result for dividing them as well. So I'm not going to show you the dividing rule, but you use a very similar process. And what you get is the modulus of z1 over z2 is equal to the modulus of z1 divided by the modulus of z2, and the argument of z1 over z2 would equal the argument of z1 take away the argument of z2. And these results here, especially with the arguments, are synonymous to the indices rules. You know, when you're multiplying powers of the same number, you'd add the powers, and when you divide powers of the same number, you subtract the powers. So when it comes to complex numbers, multiplying complex numbers, you would add the arguments, and dividing two complex numbers, you'd subtract the arguments. So if you ever struggle to remember it, try to think of indices, and you can apply that to the arguments. Don't apply it to the modulus, but you can apply it to the argument. So what I'll do is I'll put these results up on the board again for you to copy down. By all means, pause the video, take all that in, but what we're going to do is we're going to put the result up and we're going to use it to multiply and divide some complex numbers. So on the left you can see the results we came up with just a moment ago, and on the right we've got two complex numbers which I'm going to multiply together using those results. So what I want to do first is I want to work out what the answer to z1, z2 is. So the first thing I'll do is work out what the modulus of z1, z2 is, and you do that by just multiplying these two numbers here. So we can see that from here. The modulus of z1, z2 is the modulus of z1 multiplied by the modulus of z2. So that's 2 times 3, which is 6. And the argument of z1, z2, so according to this rule here, you'd add together the arguments. So it'll be pi over 3 plus pi over 2, which is 5 pi over 6. Now what I need to check here is that, remember with the Argand diagram, that it hasn't gone over here, but 5 pi over 6 is still over here because it's less than pi, so we're okay, we can still use that. So let's put it all together. z1, z2 would equal, so it's in modulus and argument form, so it'll be 6 cos 5 pi over 6 plus I sine 5 pi over 6, close brackets, and that's all there is to it. Right, next we'll look at z1 divided by z2. Okay, and what we need to do first of all is work out what the modulus of that is. And to do that, we just divide the two moduluses. Okay, so that would just be 2 divided by 3. And the argument of z1 over z2 would equal pi over 3, take away pi over 2, which is pi over 6. So z1 over z2 would equal the modulus, which is 2/3, then cos pi over 6 plus I sine pi over 6. And finally, we'll just try squaring one of them. So let's just do z1 squared, okay, and just remember that is the same as z1, z1. So let's look at the modulus of z1. Z1 squared. So it'd just be 2 squared, which is 4, and the argument of z1 squared, let's make that a curly bracket, would equal pi over 3 plus pi over 3, which is 2 pi over 3. Okay, so that means z1 squared would be 4 cos 2 pi over 3 plus I sine 2 pi over 3. And we'll do one last example, and as you can see in this one here, we've actually got 3 complex numbers multiplied together, but it doesn't change. Okay, the rule doesn't change. You can just multiply all the moduluses, so 6 times 5 times a third. So 6 times 5 is 30, and a third of that is 10. Okay, and with your arguments, because we're multiplying all these numbers, we just need to add them together. So for the arguments, let's just do pi over 10 plus pi over 3 plus 2 pi over 5. And if you did all that on the calculator or in your head, you'd get 5 pi over 6. So overall, my complex number can be written as 10. So remember, that comes from 6 times 5 multiplied by a third. And it'd be cos 5 pi over 6 plus I sine 5 pi over 6. Now what you could do at this stage is you could actually work out what cos 5 pi over 6 is. So cos 5 pi over 6 is minus root 3 over 2. So minus root 3 over 2. And the sine of 5 pi over 6 is 1/2. So that's going to be the same as 10 minus root 3 over 2. So in brackets minus root 3 over 2 plus I times by a half. So let's just write that as a half I. So plus half I, and then if I expand the brackets, I'll get minus 5 root 3 plus 5I. And one last thing before we go, let's just draw ourselves a set of axes that we'd use for the argon diagram. Okay, remember, when we're going around this way, we go up to pi, and when we go around this way, we end up at minus pi. Okay, so the angles we give when we go around anti-clockwise up to here, they're from 0 to pi. If you go around clockwise around this way, it's going to be from 0 to minus pi. But sometimes when you're multiplying these numbers together, you'll get an answer which is something like, for example, you might get something like 13 pi over 3. Okay, now 13 pi over 3 is equal to, well, if I wrote this as a mixed number, 13 divided by 3 is going to be 4 and 1/3 pi. Okay, now if there's 2 pi in one revolution, that would be 2 revolutions. So it'd go once and then once again and then 1/3 of pi. So what it's actually the same as doing is that. Okay, where that is pi over 3. So I would give my argument as pi over 3, not 4 and 1/3 pi or 13 pi over 3. So that's just one thing to bear in mind. But other than that, that's all there is to it. And next lesson, what we're going to be looking at is how to use complex numbers to solve loci problems or to express loci, and how to change from the loci, the equation of the loci using complex numbers into Cartesian form as well, which sounds like fun, doesn't it? Right, that's it, and goodbye for now.